Okay, so let's start our class today. So we stopped around here while talking about this quantile. Um, so quantile is one particular type of a function that maps the value of an f to a certain value. So it's basically an inverse function of cumulative distribution function. So you guys know what the cumulative distribution function is. So we have this x, and then this is a p. So y value is p probability of x being small x. I mean x, large x being smaller and equal to x. So this cumulative distribution function will be something like this. So the maximum value will be exactly 1, and then it will be non-increasing function, right? So in this case, we can kind of think about this CDF. If you are more familiar with this, the PDF, the probability density function. So if you think about some kind of Gaussian density function, and then we are familiar with what the meaning of this Gaussian density function means. And then if we consider the integral, so if x was 3, and then the CDF, so in this case, we consider this probability density function, and then after from this function, we obtain this CDF into this form. So this is defined as this guy. So from minus infinity to up to 3, we consider this integral. So it means the area under this curve up to the x value of 3, if this area is equal to 0.7, then we have a y value or function value of the CDF as 0.7. Okay? And then you guys know this meaning of CDF, and then we can also think about the inverse relationship. So we now give the y value. So what if we give an input value of a 0.7, and then our new function will give the x value, the corresponding value of an x, okay, which is corresponding to this value. Okay, so this function is what we call this quantile. So we have some sample that describes our probability density function, or this kind of cumulative function, probability function, and then what will be the x value? What will be the x value that have the probability of 0.6, okay, based on this equation. Okay? Okay, so that is the meaning of this quantile, and this function, called the quantile. So let's think about this sample. So we suppose we have sample of 3, 8, 6, 5, 2, 3, 1. So in total we have, so let me add another sample of 0. We have 8 points, or 8 data samples, right? And then what we do basically is to just sort them out in an increasing order. So we have 0, 1, 2, 3, 3. So we use these, okay, and then 5, 6, 8. And then what will be the probability, the quantile corresponding to 1/8. So we have to consider what is the value in this place, so that our cumulative density function is summed over this range, and this sum integral value is equal to 0.8. 1/8. Okay. So in this case, what will be such value in this place? So in this case, it will be 0, because if we consider this integral, inclusive, so we include the 0, and then from this sample, if we consider this cumulative function value, and then it will be 1/8. Okay, and then what will be what will be this value? Okay, so in this case, so we have a sample, so the probability will increase by the amount of 1/8, right? But this f value used in this quantile function can have any value, and from this definition, okay, minus infinity and some value, and then p of an x and dx. And so here, when talking about this quantile, this value is chosen from one of our samples. So in this case, we have to choose one of these samples, like 0, 1, 2, 3, 3, and 5, and so on. And then what will be this corresponding value that will make this expression as 0.26. Okay. So so in this equation, it may not be exactly true, but let's look at this definition of this quantile. So specified fraction, which in our case is 0.26. Okay, and then this is probability value is less than the actual probability. So this one will become like this. Okay, so among all the values satisfying this equation for those values, and then we choose the smallest one. So up to this point, the probability was 1/8, and then up to this point, okay, by including up to 1, the probability will be 0.25. Okay, and then up to 2, we have 0.375. So the answer will be, here in this case, we have the answer as 2. Okay, so by including up to 2 as an x values, we now can reach the probability that is greater than or equal to the specified probability value f. So this is the definition of quantile. So basically, quantile can be understood as an inverse probability, inverse function for this cumulative density function. Okay, and so this is basically a quantile plot. So depending on the probability value that we call f or fraction, and then we can map this quantile or the probability value into a corresponding x values, and then those coordinates between the fraction and the coordinate value will form one single point and then another single point and so on. So that way we can obtain this kind of quantile plot. And then this function is basically an inverse of cumulative distribution function. So if you think about the reflected version of the curve with respect to this linear function of y equal x, and then we can think about this flipped version of the curve, and then this flipped version of the curve will be your cumulative distribution function, because they are having the relationship of this inverse functions. Okay, so that is a quantile plot. And then now we think about this normal quantile and quantile plot. So we learned this quantile plot, and then this normal quantile plot. So we see quantile 2 times, right? So in this manner, the meaning of this quantile plot, or in short, we call this as a QQ plot. So in this case, this curve for this QQ plot will have x and y axis as both quantile values. So what was a quantile? So quantile maps the probability value into some value of an x. Okay, and then we now think about 2 different random variable and their probability distribution function. So let's consider the random variable of an x1 and x2, and then suppose this guy has, for example, like density function of f1 of an x, and then the cumulative density function of p1 of an x, and then in this case f2x and p2x. Okay, and then so basically, when considering each of these cumulative distribution function that maps the x value into a certain probability value, and then we have these 2 different functions, and then we can also consider the inverse function for each of these cumulative function. So let's think about this inverse function, something like this, p2. Okay, so the meaning of this is, so for random variable x1, if we consider the probability of 0.1, and then based on this mapping, the inverse of cumulative distribution function, what will be the corresponding value of x1? Okay, so let me give an example. So we suppose we collected all the man's height, and that is the random variable of x1, and then woman's height is called random variable x2, and then you can construct its cumulative distribution function, and then you consider the probability of 0.1 and then its corresponding height for man and woman. And then so suppose this was man and this was woman. So for this case, let's suppose this value was mapped 160 centimeter. Okay, so that means for men, the lowest, top 10, lowest 10% of the person, the 10% of the shortest person among all the men, the height of that man is 160 centimeter. Okay, and then we can also think about the corresponding woman's height that has actually the lowest 10% among the women's height. So in this case, yeah, I mean, in practice, in reality, whether will this value be smaller than this or larger than this? So the question is whether this value is bigger than 160 or smaller than 160. Can anyone answer? 어디서 포인트 주기 너무 쉬운데. Yeah, can anyone answer? So, yeah, do you think if this value is smaller than 160 or larger than 160? Smaller or larger or taller? Eh? It should be smaller, right? Yeah, so let me make the example more simpler. So you collected 100 men's height and also 100 women's height. And then you sort them out, and then you consider the 10th ranked person's height among men's, and also the 10th height among the woman's height. So this 10th height is corresponding to 160 for men, and then 10th person's height is some value like 155, for example, right? So this value will be likely smaller than men's height because usually woman is shorter than men, right? Okay, so here from this mapping, we mapped the exact same value of a probability, and then we mapped into the corresponding x value for the two different random variable x1 and x2. Okay, and then we consider this as a one single point in your two-dimensional plot. Okay, so this is a man's height, and then this is a woman's height, and then one single point is formed based on the same probability value. Okay, and so let's see, it's 160, and so this is 155, and then we draw one single point, and then what about the value when changing this value with 0.2? Okay, so it's like identifying or obtaining the 20th person's height for men and women. And then suppose that value was something like 163, and then 157. Okay, so definitely these values, and each of these values will be monotonically increasing, and then the next point will be 163, and then it should be 155, and then 157, we have another point. Okay, so that way we can draw this quantile plot where each of x and y axis are mapped to two different quantiles for the different random variables. Okay, but this probability will be the same. I mean, the same probability will be used to form each of these points. Okay, and then and in this case, the quantile plot can be shown in this form. So like this. Okay, or some quantile plot will be something like this. Okay, so let's consider these two different cases, and let's first consider this red case, and then it means, so this point was corresponding to the same probability value of 0.1, and this point has the same probability of, for example, 0.15. Okay, so in this case, the velocity of increase, I mean the amount of increase in terms of a woman's height was much faster than the increase in terms of a man's height in order to achieve the same probability increase, right? So that means which one has more probabilities? Okay, sorry about that. Oh, okay. So in this case, in order to increase the same amount of probability, the woman needed to increase the shorter distance. I mean, shorter amount of x values, right? So that means the let's see. Okay, so in this case, this is a woman's height and this is a man's height, and then the probability assigned to the range between 155 and 157 was the same as the probability assigned to 160 to 163 for men's height, right? So in this case, the same probability was assigned to a wider region in the case of men compared to the women's case. So again, the probability increase was staying the same, right? Probability increases from 0.1 to 0.15, okay? In order to achieve this same amount of probability, the woman needed much smaller increase in terms of an x value, right? So that means overall the height, okay? So height was like higher than this value because we are talking about the probability density function. So suppose we have some density function of woman's height like this, and then this is another density function for men's height that has another Gaussian distribution, for example. Okay, but the integral over this region should be the same as 0.15 minus 0.10, right? So this probability difference should be assigned to this region and this region, right? But the same probability should be assigned to wider range of an x value compared to this men's case, and that this means overall the height. So if we just simplify this case as just a rectangle, okay, so let's just approximately simplify this shape as just a rectangle, and then since we have a wider value, larger value for this width, and so the height should be smaller here in this case than in this case. That means in this part the probability is increasing faster. Okay, so that is the meaning of that is the information that we can obtain from this kind of graph. So again, if we think about the quantile plot, like having this kind of shape, but around this region, in order to achieve the same amount of a probability increase, the velocity for this x1 is much faster than the velocity of x2, right? And this means the x2 has more probability, right? Within a shorter, within the short amount of an x value. Okay, so that is what we can obtain by looking at this kind of slope of this graph. Okay, so this is the meaning of this QQ plot, and then normal QQ plot is a special case of a QQ plot when we used this x1 as standard normal Gaussian random variable. Standard normal random variable. So we still consider two different random variables that has their own probability density function, but here the first one is fixed as standard normal random variable. So that is the meaning of this normal quantile plot. And let's look at the x-axis, and the name is standard normal quantile. Then okay, so there seems to be some type. There should be something wrong, I think. So let me check the book quickly. Not sure, but I think the book has something wrong. I believe this x-axis should be something like this. So let's consider this as 0 and -1 and -2 and -1. It should be 1 and 2. Okay, so this is the typical values that we have to see in this normal quantile plot. And then let's look at, for example, like this point. Okay, so this point is saying x1, x2 as 0, 34. So that means at at the value of 0 for x1 and at the value of 34 for x2, they should have the same probability value. And then since the x value, the first random variable is standard normal random variable, what is the value of this probability of x being less than or equal to 0 for a standard normal random variable? What will be the probability value for this? Okay, I'm asking what is the probability? In terms of a cumulative distribution function when x is 0 for the standard normal random variable. 0.5, right? Because we think about this standard normal random variable and x is at 0, and then when computing this cumulative value, it should be 0.5. Okay? And then this 0 is mapped with the value of y as 34. And then suppose these values were some measurement that you obtained, right? And then it means the value of 34 is exactly at the middle. So it's like a 50th quantile. Or if you consider like 100 students, and then the exam score of 34 got exactly the fifth ranked out of 100 students. Okay. Okay, and so this is the meaning of this normal quantile plot, and then So by looking at this slope of each graph at different points, we can see this random variable x2 is increasing faster or smaller for its probability value compared to x1. Okay, so intuitively, if the probability increase is, the velocity for this probability increase is exactly the same as the normal standard normal random variable, and then this normal quantile plot for x1 and x2 will follow exactly a line. Okay, exactly a line. But if this quantile plot has this kind of shape or this non-straight shape, and then this means compared to the normal distribution from this slope, the probability is increasing slowly for x2 compared to the normal distribution at this point. But yeah, see. But at around here, the slope is much less than 1. So in that case, the probability is increasing much faster for x2 compared to the normal standard random variable. Okay, so that way, by setting the x1 as a standard normal random variable, we can kind of compare visually how different the distribution of x2 is from the normal, standard normal random variable. Okay, so this is something called normal quantile plot. And then, there are some examples, and I think that's it for this normal quantile plot. Okay. Okay, let me, before finishing this part, let me just add one more thing. So, in practice, when drawing this quantile plot, we cannot consider all the different probability values. So, in this case, we thought about the probability of point 1, and then we considered point 2 and point 3 and so on. And then at which probability value should we obtain those quantile values? It can have infinitely many values. So we can just use 0.01, 0.02, 0.03, and so on. Right? So in this case, we should obtain 100 different two-dimensional points like this. And then we can obtain even more samples. So in practice, people made some suggestions so that they only obtain those quantile values when the probability value has this specific value. So here I is some integer value, and then depending on your sample size n, this probability value that you have to consider the quantile is following this discrete value. So I becomes like 1, 2, 3, and so on, and then this fi's will have their own discrete values that have this finite number of values. Okay, so that's it for this quantile plot, and then also that is the end of chapter 8. Any questions? 요거요. 그러니까 아까는 그 probability를 뭐 0.1, 0.2, 0.3 이런 값들을 기준으로 해갖고 그거의 역함수에 해당하는 x1과 x2를 이렇게 구해갖고 포인트를 찍을 수가 있다 그랬잖아요. 근데 그 포인트를 우리가 몇 개를 이제 구할 거냐, 몇 개의 포인트들을 계산을 할 거냐 측면에서는 뭐 사실 무한정의 probability, 서로 다른 probability 개수를 가지고 그거에 해당 그 퀀타일 밸류들을 가지고 오면 돼요. 근데 그게 이제 무한정 그렇게 하기는 또 힘들고, 그리고 이제 누구는 뭐 0.1 단위로 하고 뭐 누구는 0.05 단위로 하고, 이런 값들이 뭔가 좀 중구난방으로 쓰여지는 거를 좀 방지하고자 사람들이 뭔가 약속을 했어요. 그 probability value를 어떤 이런 식에 의해서 그런 디스크리트한 레벨을 쓰자. 그래서 예를 들면 n이 예를 들면 뭐 한 샘플이 5개다. 그러면 5개면 값이 5개이고, 그러면 퀀타일은 그 probability를 굉장히 세세하게 따져봐야 저거는 썩 의미가 없어요. 왜냐면 우리는 5개의 샘플만을 가지고 이제 그 cumulative distribution 펑션을 생각을 해야 되니까. 그래서 그것들을 이제 n이 커지면 커질수록 더 세세한, 더 이제 자잘한 어떤 디스크릿 레벨에서 그 퀀타일을 따져보자. 네, 그런 식으로 뭔가 식을 어떤 적당히 만들어 놓은 게 이런 식이에요. 근데 왜 하필 이게 이렇게 복잡한 형태를 띠고 있느냐? 뭐 이게 어떤 이론적인 뭐가 이유가 있대요. 네, 그리고 이게 이 포인트들이 그러니까 어떻게 생각할 수가 있냐면, 노멀 디스트리뷰션에서의 그 어떤 기준을 우리가 따지는데, 그 노멀 디스트리뷰션에서의 그 probability value들이 좀 뭔가 좀 센서티브하게 이렇게 변화하는 그런 대표 포인트들을 적당히 이렇게 뽑았을 때 어떤 그 근사적으로 저런 식을 가지더라. 그래서 저 지점에서의 어떤 그 퀀타일 밸류들을 우리가 생각을 하는 게 좀 좋더라 라고 해갖고 누가 이제 하나의 저런 식을 만들어 놓은. Any other questions? Okay, so we are now entering chapter 9. And we are 1 minute left. Okay, so let me introduce maybe 2 of the important concepts in this chapter. Okay, so the first one is unbiasedness. So unbiasedness is as follows. So in the previous chapter, we considered this x bar, right? And then x bar had its own distribution. So x bar, when x becomes large, and then x bar is following the normal distribution, so that theorem is called central limit theorem, right? But anyways, if we consider this kind of a sample mean, or in general, this is called statistic, right? So we have sample, and then each surveying company collects their own sample, and then they compute the statistic as a kind of function value, right, from their own samples. And then this statistic, or this kind of function values, will have their own probability distribution. But here, suppose your goal to compute the sample mean or the statistic is to estimate some parameter in your underlying distribution. So what is the meaning of this x bar? Or, yeah, how can we utilize this information? I mean, in order to understand the underlying probability about xi or individual x, right? So this one is approximately telling you what the true mean is, right? So we consider the true mean mu, and then this one can be kind of viewed as our guess about this true mean mu, right? But again, x bar is a random variable, and that has its own probability distribution function, right? And then this x bar, since it is just a random variable, it has its own mean value, or the expectation value of x bar. And then if this statistic and its expectation value from its own distribution for this x bar, if this expectation value is actually the same as the true parameter that you want to estimate using this x bar, so if you can satisfy this equation, and then this is called unbiased estimator. Okay. But yeah, suppose let's think about the other situation where your estimator or your statistic is biased, not unbiased. In this case, it is saying like your sample mean is is generally overestimating your true mean. So the true mean was 170, but your sample mean is generally telling you the larger values than the true mean 170. In that case, you are kind of overestimating the true mean value, right? On average. So in this case, your estimate is biased, right? Because it's telling you the a little larger values than the true value. So that's the notion. Yeah, that is this notion of unbiased estimator. Okay, that's it for today. 네.
너무도 멍청하게 6 곱하기 3 곱하기 6 곱하기 5를 180이라고 했어요.
네.
이거는 그 계산 실수로 감해 주실 수 없나요? 이걸 90으로 해서 더했으면 맞았거든요. 근데 제가 이걸 착각해가지고 180으로 했어요.
이거를요.
네.
그 부분을
네.
나한테 사진을 찍어서 이메일로 좀 보내주세요.
아, 예, 그러면은 맞게 해주시나요?
아, 그러면은 내가 조교랑 그거를 잘 같이 이야기해보고 다시 알려줄게요.
아, 네, 알겠습니다.
쿼타일 할 때고
네.
Q 그 데이터 8개 있고 Q 0.26 계산하는 거 있잖아.
네.
그거는 답이 어떻게 되나? 그냥 0.25랑 똑같이 계산하면 돼.
네. 맞아요.
그리고 이게 그 점수를 다 합하면 82 계산이 되는데
네.
그 블랙보드에 80이라고 나와서
아, 그래요?
잘못